Hello everyone, this is Vasishta from Aerobee section. Today I am going to explain about iron carbon phase diagram from aircraft production technology subject. Coming to the iron phase carbon, there are some definition of some structures inside the iron carbon phase diagram. The, the various phases that appear on iron carbon equilibrium phase diagrams are under austenite, ferrite, pearlite, cementite, masonite, lead These are the structures that are the main structure of a iron carbon phase diagram. So coming to austenite is an interstitial solid solution of a carbon dissolved in gamma F gamma FCC of a iron. Maximum solubility is 2% carbon at 100 and 1130 degrees Celsius. It is high formidability. Most of heat treatments begin with this single phase. It is normally not stable at room temperature, but under certain conditions, it is possible to obtain austenite at a room temperature. So, austenite. Here, the maximum solubility of an austenite is 2% at 1130 as we have seen earlier. So, the average properties of a austenite are given with the tensile strength, elongation, hardness, and toughness. So, as we can see, the tensile strength of austenite is around 15,000, 1,50,000, 1.5 million SI. As we can see, this is the structure of austenite. And elongation is 10% in 2. Hardness are 10% in 2 in carbon 40. Hardness is Rockwell and toughness is high. And coming to the ferrite is also known as alpha solid solution. It is an interstitial solid solution of a small amount of carbon dissolved in alpha BCC iron, stable form of iron below 912 degrees Celsius. The maximum solubility is 0.025% at 723 degrees Celsius and it dissolves only 0.008% carbon at room temperature. And average properties are Average properties of ferrite include tensile strength, elongation, hardness, and the tensile strength is 40,000 psi. Elongation is 40% into carbon, and hardness is Rockwell. This is the structure of ferrite. And coming to pearlite, pearlite is the eutectoid mixture containing 0.80% 0.80% carbon and it is formed at 723 degrees Celsius on very slow cooling. It is a very fine plate-like and lamellar mixture of ferrite and cementite. The white ferrite background or matrix contains thin plate of cementite, which is, as you can see here, the ferrite or the background and the black lines are cementite. The average properties of pearlite consist of tensile strength, which is 1,20,000 psi, and hardness elongation is 20% into carbon, and hardness is Rockwell. So the definition of structures in which cementite, martensite, and leadburite. What is a cementite? Cementite iron carbide is a very hard, brittle intermetallic compound of iron and carbon as Fe3C. Contains 6.6% of carbon. It is the hardest structure that appears on the diagram. Exact melting point is unknown. Its crystal structure is orthorhombic. It has low tensile strength, which is 5000 psi, but high compressive strength. Martensite, a supersaturated solid solution of carbon in ferrite. It is formed when steel is cooled or so rapidly that the change from austenite to pearlite is suppressed. The interstitial carbon atoms distort the BCC ferrite into BC tetragonal structure, responsible for hardness of quencher steel. Supersaturated solid solution of carbon ferrite is martensite. Ladybirite is eutectic mixture of austenite and cementite. It contains 4.3% of carbon and it is formed at 1130 degrees Celsius. Iron carbon diagram, a map of temperature at which different phase changes occur on very slow heating and cooling in relational to the carbon is called iron carbon diagram. The map of temperature with the different phase changes occur on very slow heating and cooling in relation to carbon is called iron carbon phase diagram. Iron carbon diagram shows the types of alloy formed under very slow cooling, proper heat treatment temperature, and how the properties of steels and cast irons are formed. Cooling curve of pure iron. As you can see, the graph for temperature and time. As the temperature is decreasing, the time is also get increased. So at 2800 degrees Celsius, we have Fahrenheit, we have liquid, and also from the delta ion, gamma ion, which is non-magnetic, and body center cube, body cubic center, phase cubic center, 90. So various features of iron carbon diagram, FEC diagram. As we can see, this is the iron carbon phase diagram at which the temperature and composition of with carbon is also given. The iron carbon phase diagram from here we have maximum solubility of carbon in ferrite is 0.022%. Maximum solubility of carbon in austenite is 2%, at which from 400 degrees Celsius to 1600 degrees Celsius, and from 1000 Fahrenheit to 2500 Fahrenheit, we have different types of compositions, and we have delta ion exists between 1394 degrees Celsius and 1538 degrees Celsius. It may exist in combination with the melt to 0.5% with carbon, with austenite to 0.18% and with carbon, and in a single phase state to 0.10% with carbon. Delta ion has the BCC crystal structure and its magnetic austenite, and is also known as gamma ion, interstitial solid solution of carbon up to 2.1% weight percentage dissolved in iron with the FCC structures stable up to 1394 degrees Celsius non-magnetic phase. Ferrite, alpha ion, which is an interstitial solid solution of a small amount of 0.022 of carbon dissolved in iron with the BCC crystal structure, possesses polymorphic transformation to gamma ion at 912 degrees Celsius. It is softest structure of iron carbide diagram, magnetic below 768 degrees Celsius. Cementite is also an iron carbide, which is Fe3C, contains 6.6% of carbon. It is typically hard and brittle interstitial compound of a low tensile but high compressive strength. Its crystal structure is orthorhombic metastable phase at 700 degrees Celsius slowly and decomposes to alpha iron and carbon. And we have, and this is the iron carbon diagram with compositions of temperature Celsius and temperature Fahrenheit. Here we have gamma plus Fe3, which is here we have cementate formation, we have ferrite fermentation, and it is austenite formation. So the three-phase reactions: peritectic, eutectoid. Peritectic is at 1490 degrees Celsius with low weight percentage of carbon alloys, and eutectic is at 1130 degrees Celsius with 4.3% of carbon alloys called cast iron. And eutectoid is 723 degrees Celsius with eutectoid composition of 0.8% carbon. Two-phase mixture, ferrite and cementite. They are eutectic, eutectoid, and peritectic. Peritectic, which is liquid and one solid phase transformation is to a second solid phase. Solid plus liquid is solid, and gamma delta plus liquid, that is iron plus liquid, gives with cooling and heating we have beta. Eutectic, liquid transform to two solid phases. Liquid from cooling and heating we have alpha plus beta. Eutectoid, one solid phase transformation to two other solid phases, which is solid and solid plus solid, which is alpha plus Fe3. In austenite perlite mixture of ferrite and cementite, we have, as we can see, it is alpha plus alpha plus ferrite. It is austenite. We have austenite liquid plus austenite plus cementite, ferrite plus cementite, austenite, which is perlite. Here we have perlite, we have austenite, and here we have alpha ferrite at here. Detector reaction. As we can see, the formation of perlite structure nucleating at gamma grain boundaries, growth by diffusion of C2 achieve the composition of alpha and Fe3C is structural change alpha lamellar matchstick redistribution of carbon by diffusion austenite ferrite cementite austenite with 0.76 percentage, ferrite with 0.02 percentage of carbon, cementite is 6.70 percentage of carbon diffusion. We have growth direction on perlite cementite, which is Fe3C austenite boundary. Transformation in relation to FEC diagram. We have austenite, ferrite, and cementite. Transformation of FEC diagram. In order to understand the transformation process, consider a steel of protected composition 0.8% carbon being slowly cooled along the line x minus x to x. At the upper temperature, only austenite is present with 0.8% carbon being dissolved in solid solution with FCC. When the steel cools through 723 degrees Celsius, several changes occur simultaneously. The iron wants to change crystal structure from the FCC austenite to the BCC ferrite, but the ferrite can only contain 0.02% carbon in solid solution. The excess carbon is rejected and forms the carbon-rich intermetallic known as cementite. Nucleation and growth of perlite. As you can see, the austenite and with the nucleus cementite will form the formation of the ferrite, and we have perlite. Austenite microstructure for steel. It is the austenite structure, and the schematic picture for formation and growth of perlite is given here. And cemented structure is and martenite structure is cradle-like structure. The ferrite phase is crystal structure with BCC, and so it is soft ductile magnetic. Austenite is FCC. Soft moderate strength non-magnetic. Cementite is compound of iron and carbon. Fe3 and hard bed. Iron carbon alloys of 2%. Cast iron is iron carbon alloy of 2% of carbon. More are cast irons. Typical composition 2 to 4% and 0.5 to 3% Si. Silicon less than 1 of manganese and less than 0.2% of sulfur. And silicon substitutes partially for carbon and promotes formation of graphite and carbon-rich compound instead of Fe3C. The summary of a given iron phase diagrams are used for tools to determine the number of phases, that percentage of each phase, and the components of each phase given T and component of the system. Binary eutectics and binary eutectoids allow the range of microstructures with different properties.